Hi everyone and welcome to Chem class. Today we're going to look at polar bonds and polar molecules and comparing them to non-polar ones and how we can work out if they are polar or non-polar and how we can represent that in a diagram. Let's look at our first example. First example is chlorine gas. Now we know that the way that is structured is you have a chlorine atom that is sharing one pair of electrons to another chlorine atom. Now for ease, I've listed down here some of these atoms that I'm going to be using today and what their electronegativity values are. We see that chlorine is 3.2. That's fairly high. So let's just put that in, 3.2, 3.2. So what we have here is an atom that really wants to pull electrons towards it, but we have an identical one doing exactly the same thing. So this is like a tug of war between Dwayne Rock Johnson and his clone. So we know that they're both equally pulling on the electrons, which means that we don't end up with a difference of electrons at one end more than another end of the molecule. So this is a non-polar bond and a non-polar molecule because it's just a nice simple linear one. So let's just label that. We do not have to indicate a delta positive and a delta negative end or a net dipole in this because there is no net dipole. We don't have poles to this molecule. Okay, let's look at another example. You've probably seen this example as well. We have a hydrogen atom, it's a linear molecule, and it's covalently bonded to a chlorine atom. Let's look at these electronegativity values. We now have a 2.2 for the hydrogen and our 3.2 for the chlorine. So what we have here is a difference in electronegativity. What that means is that the chlorine is, let's say, hogging the electrons. It's pulling the electrons more towards it because it's stronger in electronegativity, which means it has a greater affinity for electrons. They want to sit closer to the chlorine atom. So what we can do is we can indicate that net dipole with this particular type of arrow. The arrow is showing you where the electrons want to sit more towards. They want to sit more towards the chlorine. This becomes then what we call a polar bond and a polar molecule. Polar means there are poles. It has a pole that is more negative because electrons are negative and they want to sit more towards that end. So we can indicate that with this funny little symbol, a delta negative. And we can indicate that conversely, the hydrogen becomes a delta positive. This is not the same as a cation and an anion. The delta indicates like a partially positive and a partially negative charge. They are different because if it was a cation and anion, they would have ripped those electrons away and kept them, and this one would have completely lost the electrons. That's not the case in this molecule. The case is the electrons are just spending more time down at the chlorine, making it kind of feeling more negative than the hydrogen is. So we label this as a polar molecule. Let's look at another example where we've got something a bit more exciting. We've got a few things to look at here. Let's look at this particular example. Sorry, this is our CH4. Now the reason I want to look at this is because we can examine a bond and then we can compare it to the molecule. So let me just pull that out. This particular bond, let's get our net electronegativity values, 2.2 and carbon is 2.6. So we see the carbon is more electronegative, which means of course there's going to be a pull of electrons towards that end. It means that the carbon is a delta negative charge and the hydrogen is a delta positive. So again, the electrons want to sit more towards the carbon. It makes it a bit more negative. So this is what we call a polar bond. Okay, but then let's look at it in the molecule. What that means is all of these hydrogens here have a 2.2 electronegativity value. 2.2, 2.2. And the carbon has that 2.6. So if I take this and put it back in here, what we have is all these electrons want to sit more towards the carbon. But what we're trying to identify now of this molecule is it a polar molecule? We know the bond inside it is polar, but is the molecule polar? Now, you might have heard in class that you need to ascertain whether the molecule is symmetrical or not. Because when we are identifying that something is polar, what we're saying is there are poles. You know, like a north pole and a south pole, there are ends to the molecule, and those ends have a different experience. But in this, the carbon is trapped in the center. It's a symmetrical molecule. Every single end of the molecule is this 2.2 electronegativity value of hydrogen, which means that you can't come into any part of this molecule and feel that one end is more negative than the other, because in fact all these hydrogens are having electrons pulled away from it. So every end of the molecule feels exactly the same. So what we have though is a polar bond inside a non-polar molecule. As I said, because it is a symmetrical molecule. So again, it's like every end here is tug of warring, but these are the really weak opponents, and they're all having electrons move away from them to the same extent. So there's no poles in there. Let's have a look at another example. One last one that's a little bit more complex again. Let's take our PCl3. So the Cl's are 3.2 and the P is 2.2. We can see again that there is a difference in electronegativity. The electrons want to sit closer towards the Cl, so we would put that on every Cl, knowing that the electrons want to sit closer to there, and that tells us that they're delta negative chlorines and a delta positive phosphorus. Okay, so this molecule is not symmetrical. We actually do have ends to it. And an easy way to sort of see that is if I sort of put a bit of a dotted line to show you that this end of the molecule has this delta negative charge, and this end of the molecule has a delta positive. Another molecule coming in can feel that this side is more delta negative and this side's more delta positive. So because of that, we have not only polar bonds in this molecule, but it's also a polar molecule. It's asymmetrical, and we have uneven sharing of electrons, so that one end is feeling more of those electrons than the other end. Okay, hope that helps.